Hello, my name is Demilola Onikeku. This is our chemistry homework assignment.
And I'm Sophia Lam.
In this assignment, we've been instructed to work with the rocket science in SpaceX. For my part of it, I've been assigned to construct a spectra for the mixtures of combustion of methane, which is used for rocket fuel. For the infrared spectra, I used the reference spectra from the NIST chemistry webbook that was given to us as an example. I first looked at uh, the main product, not products, the main ones for methane and oxygen, which is if you scroll down right here, you can see them. The top one is the methane and oxygen. Well, you cannot see oxygen because it is not a homonuclear molecule, so it will not show in IR spectrum specifically. But you can see the methane, you can see the peaks of it and all that. The bottom one shows the product of the product of the IR spectra, which shows the carbon dioxide and the water, showing the peaks and all of that. And for the stoichiometry that I talked about, the explanation, I said that methane combusts according to the balanced reaction CH2 plus 2O2 going into CO2 plus 2H2O. In the reaction mixture, methane shows R absorption due to CH stretching and bending vibrations, while oxygen does not appear because it is homonuclear, it does not change dipole moment. After combustion, methane peaks disappear and new peaks corresponding to CO2 and H2O appear, including strong OH bond stretching from water and asymmetric stretching from carbon dioxide shown inside the chart. You can see the difference between the two, the product and the normal infrared spectra. Moving on to the step two of the X-ray spectroscopy of the engine residue. We were asked to see the residue during an engine test from copper and carbon. As you can see in the chart, I wrote down each peak from showing the wavelength on the bottom and the residue at the top. It shows the top one having the most spikes being the copper, oxygen, which is just naturally in the air. We use that as a baseline. So it shows those spikes, and then copper or carbon at the end, bottom, which has the least amount of binding energy inside of it.
And then for part three, we found the mass spectrometry for rocket fuels. And there's two different types of rocket fuels. There's the natural gas-based rocket fuel, which is what Starship uses, and a kerosene-based rocket fuel, which is what Falcon uses. And this top graph shows the natural gas rocket fuel, the mass spectrometry for the natural gas rocket fuel. And as you can see, natural gas is mostly methane, which is CH4. So our mass spectrometry has a peak at 16, and then it goes down at 15, 14, 13, and then 17 as well as we remove the hydrogens. And then for kerosene, it's much more complicated because kerosene is a mixture of hydrocarbons, and since it's a long chain of hydrocarbons, it's not as clear as the mass spectrometry for natural gas, which is why we see lots of fluctuations here in the second graph. And then as for the next task, which was to discuss the typical fuel composition of each, for natural gas, it contains mostly methane, as I mentioned before, with small amounts of other light hydrocarbons, but methane is around 90 to 95% of what natural gas is, and it's usually highly purified, so methane dominates the spectrum. And then for kerosene fuel, it's a mixture of hydrocarbons, as mentioned before, which is also cycloalkanes, and because small amounts of aromatic hydrocarbons are in there, it contains many different hydrocarbons, and the mass spectrum, as mentioned before, is more complex. And then here are the major peaks for natural gas based rockets. We saw in the graph that it peaks at 16, and as we remove hydrogens, it goes down to 15, 14, 13, and 12. And then for kerosene, it peaks at around 43, and then it goes to 57, 71, and 85. And here are the explanations. 43 is where it peaks. Because it's a common hydrocarbon fragment. And then 57, it's a strong alkane fragment. And then for 71, it's a larger hydrocarbon fragment. And then for 85, it's a long chain alkane fragment. And that concludes our presentation.